Okay, so I want to talk about constructions. Constructing a paradoxical graphs, a paradoxical graph. When can
Also due to advantage?
no, his friends. This is a Ram and Spencer. I think it's like 68 or something. It's old. Yeah, it's the same. Well, yeah, the same now. I mean, he was married to a Chang, but it's a different last name. Yeah, so it's the same guy. He appears in many places. There's a lot of algorithms. He wrote the book with Roga about algorithms. And I mean, we're not going to do the construction now. We have to go back. I'm going to do the preliminaries, but this construction is going to be quite close to that. We're going to have maybe a 4 to the k times this. So it's quadratic. This 2 to the k times k squared, by the way, regarding low bounds, I should say 2 to the k is kind of an easy low bound by induction. And k times 2 to the k low bound is a paper. And I don't know if it was improved to k squared. So I don't know if it's right. But so that's the distance between low bounds and probabilistic method. As far as probabilistic method versus this construction, we are going to have a quadratica, and I don't know if it was. I checked, I couldn't find it. But before doing that, I'm going to, in these 10 minutes, I'm going to do some preliminaries because the construction of that is based on one of the most important results, like in mathematics. Essentially, I mean, you can infer it from the it's kind of the Weil band, but you can infer it from things we talked about the division of the points. So I want to show that one. I will use the Weil's theorem. You'll see. So it's really deep. I mean, it's not easy construction. So I mean, it's easy construction. The analysis is basic. Okay. Also, given what it uses as a black box, it's still very interesting as an analysis. You'll see. Has some idea, which in my field they call algebrization. We take a combinatorial thing and find something algebraic and can do concepts. We'll see all of that, but before that, I'm going to need to remind you some stuff. That you really don't know. So I just need 2 definitions from groups. Those who never saw groups might not encounter them, but if you did learn group theory, these are the 2 things you see in the first or second lecture. So the first definition is about the order of an element. So if G is a group, not a graph. We take G and G, then the order, it's a very basic definition of G, is the least number such that say it's a multiplicative group. So it's the least number such that if you multiply G with itself that many times, you go back to the unit element. Of G is not the middle of G is the least number K, it exists. Well, I guess larger than 0, such that G to the K is E. Sometimes they don't exist. Integers, in addition, one doesn't have a finite point. But if you look at Zn, for example, in addition, then every element has order which is most. Right, so for example, maybe we should do it's fine. And the second definition is a cyclic group. A group is cyclic if there exists some element such that the entire group as a set is the same set as G to the K, where K go over all the integers. It's enough to do this. I need that?
Yeah, because like also the inverse.
Finite groups, there is no issue. Infinite groups, uh, maybe okay, because finite. Right, for finite order, that's what I can find. Right. So let's just for me to make sure it's all finite, okay? And then and check. Which should we see? Because then one you have take the negative. So that depends if you want to check. For finite groups, definitely there is no difference. So it's N. For finite, it could be N or it could be Z. Infinite, actually, no. For me, in my head, like, yeah, this should, I mean, no, I can't live in a world where 0 is not 60, so then I have to take a Z, I guess. But maybe it's one of these things that some people, they're like, people have opinions about. But, yeah. I think it's that. So let's just open this as the moment to buy. Good. So for the lecture, let me just tell you one thing about finite fields, which I did say. So just an observation, because you don't think in terms of groups. A finite field, or any field, but let's say a finite field, is just two groups. Plays nice to each other. That's a formal thing. So what do I mean? That's a field. We have two operations, and then there are like 7 or 11 depending on axioms for fields, but actually they're only like you can take it in 3 sentences. Possible is you want field actually is the following. You want not only the multiplicity structure, you want the field, only the addition structure to be a group. It also should be commutative. Should be a group. Commutative group. A plus B equals A. So that's if you can break it down, it's like 4 axioms. There is a unity, there is a unit element which is denoted 0, you have associativity, you have commutativity, and there is an inverse. So it's 4 axioms. This is the commutativity. What about the multiplicative group? Or what about the multiplication?
Just remove the 0.
Exactly. So you want that the multiplicative group, so you want that it will take the steps, the field, remove 0, and under multiplication it's going to be a multiplicative. And it's also going to be. So that's called the multiplicative group. And 1 is the unit there. You have to remove 0 because otherwise, I mean, like 0 and 1 are just 2 units but of different groups. Interesting. So here you have like 8 axioms for this 4. And then the last one, depending again how we do it, but you want some relation. That's the place nicely with each other between addition and multiplication. And then you want the, I forgot how they call it. So on this thing, in cost of commutativity, you don't have to argue for the second one. Right, so this kind of holds the relation between the two groups. And the one fact that I will need, what it is, it's completely trivial. I can put it in 10 minutes, but not no less. Is that, well, clearly this is a cyclic group, like 1 generates everything here, but it's not that this is fit. Zero doesn't. It's kind of, actually it's helpful. One, which is the unit of the multiplicative group, generates the additive group. Because that's relation, because one otherwise doesn't. It's not like that. And zero, it's not like zero is going to generate this thing, right? It's not even there. So it's not clear that this is a cyclic, but it is. That's not an issue.
This cross.
Right. That mine is. So I'm not going to prove that, but we're going to use them. It's a bit surprising. You don't believe me even.
No. And the cyclic so
Yeah. Yeah, there it's right. No, here there is a problem with even the small. How do you say it's small? The magnitude, like right. It's not Aleph zero. So you can't be cyclic because then you're right. Yeah. No, but only for finite. Maybe also. I think you can generalize that to any group. Well, I don't remember. Every element has some order. Maybe that's why you do it. Maybe some countable orders. I don't remember exactly one. So there is a generalization that also to infinite situations when it's a group cyclic, but definitely for finite it works. So the construction is going to be based on characters. So last time we talked about characters in the context of Paley. So now we're going to talk about characters in this context, which is not, these are graphs, not directed graphs, not Paley graphs. So let me just tell you, it's not a real definition, but more of an playing that we use. So characters are of groups, of fields, but a field is just two groups. So the characters of a field are just the characters of the groups. But we call these the multiplicative characters, for these are additive characters. But sometimes, I'm not sure it's actually completely universal, but sometimes when you just say character, you mean the multiplicative character. So we are going to say the character of a field is really, a character of a field is really just the character of his multiplicative group, where you also define this character at zero, which is the one you don't define to be zero. Okay, so character, if you want to be more multiplicative character, it's not just a character of a field. Right, so I need to give you a function from f to so we actually saw that it always has no one. The complex numbers we need here is a character in the way that we define it as a group character of the multiplicative group, where we set kind of artificially kind of 0 to be 0. Right, because it's not defined as 0. One is not to make too much headache. And we know that the character doesn't go to 0 for the rest of the elements. They go to the unit sphere, etc. So that's when you say a character of a field, you mean that. But actually, people work with characters. Also, these characters try to understand the relation between the additive and the multiplicative. But for us, let's just consider the characters. Here the characters, and we won't touch the additive. They require that all of them, No, but then I have to for non-zero. Well, that's okay because it's a multiplicative character of the character of the multiplicative group, then we require it to go to C transit. Definition. To avoid what you just said. Avoid adding the zero. So in the by definition, when you use because it comes from a multiplicative character. Maybe I'm not. When I'm saying that, I mean that chi actually is. This is an extension of a character that goes from the multiplicatives set multiplicatives group of F to the multiplicative set. So field is just two groups. Right. So you can add and multiply things and it will still be there, it's low. And also when you multiply and add, it's like used to, the relation between them. And you have the 0 as the inverse of the addition. You have 5 minus 5 will be that one. Minus is the inverse. And yeah, it's coincident. So A and B is A, and A plus B is B plus. And there are more general rings in which this doesn't always hold, and you don't have an emphasis on the multiplication and so on. Field is like the most structured. So let's do just an exercise before I'm going to. We need the 10 years, so let's go an exercise. So let's say I'm looking at the field FQ, and the character that I'm going to take is the paradoxical. Okay. The paradoxical relative one. We talked about it a little bit. So that's, I'm telling you what it is, okay? I'm just calling it chi, but it's one of the chi's. A good chi, I like it. So chi, well, chi of 0 is 0 by definition. Let me tell you what happens when you are not 0. So chi of an element, this is a non-zero element. It's going to kind of encode whether or not this thing is a square of an element. So if A is B squared for some B in the field, it's important to say for some B in the field, because when you go outside the field, you can always find such. If in the field, then it's a 1, otherwise it's a minus 1. Little what? Thanks. Q. So it's a field of size Q. So the theorem is that from any Q which is a prime power, there is a think of Q as prime. But so is it a character? It's not completely obvious. Like for a character to be a character, you need to make sure that chi of AB is chi of A, chi of B. I mean, I know how to show it, I will show it, but I don't know how to see it immediately. Because it's kind of clear. If A and B are both in this case, are both quadratic residues, then also the product is. So a kind of this will be 1, this will be 1, this will be 1. Because A and B are quadratic residues, so it's A times B. Because if A is like C squared and B is like D squared, then this is C squared. Otherwise, it's a bit, I don't know, you can convince yourself by counting somehow, but let me show you an easy way to see this a character. I call it a character. I need to explain why I call it a character. Like it's not clear that it satisfies this, meaning that it's a homomorphism for the multiplicative group to out. But I think the best way to see this, maybe you can think another way. But the best way is to remember that the multiplicative group is cyclic. Right, so what does it mean? So, also, why is this a character? So the point is that if you take the multiplicative group, as I said, same thing as g to the k, where k runs from 0 all the way up to 2 minus 1, for some g in f. I'm saying that the group is cyclic means that there is one element, there are many. There is some element, all of those powers of span, they generate the entire group. Right, so FQ star, it's not trivial that it's cyclic, but it is. Because it's cyclic, I can, instead of walking like in an abstract way of what are the elements, I can just have to fix energy. I'm really looking at like C2 minus 1. Right, you see, all the action happens in the exponent, and you just take your Q minus 1 elements in the group, Q elements in the group. So, Q minus 1 from 0 to 2. The Q minus 1 elements, I mean, right, I do either way. I mean, it's also equal.
Normally,
So that's why actually. So this is like, you see, so what I'm saying is the most statistically, basically, after you fix the generator, all the action happening in the exponent. What do you mean by action? When you multiply two things, you just add the exponents. And the exponents are, sitting between 0 and q minus 2, and the addition is modulo q minus 1. Said that the group to its size is 1. And so really, you should think of any cyclic group as z to the z of the order of the group. Anyhow, so we have this. And then just by counting, you can see that every element has exactly one representation here. So now let's see if that is see from this point of view. So now if you give me, so what are the quadratic residues? So when A is a quadratic residue, exactly. So when, right. So A can be written as g to the k, always, for some specific k in this stage, 1k, and A and phase 1, if and only if k is given. And because if k is even, you can clearly find the quadratic residue. And otherwise, you can actually show the otherwise, but you can actually also show that there are exactly half of them which are quadratic residues. Half of them are quadratic residues, half of them are not. I should say that Q is odd. Q is even. You're applying mind, and that's. Okay, then you see that it's kind of obvious because it's just you're checking whether the k that corresponds to the A is even.
excluding
Right, yeah. I rather. Yeah, that's how I like to. So chi of an element which is 1, like when it's quadratic residue, is just g to the 2k, something even. And from here you can just see that saying that this is a character translates to the fact that even plus even is even plus odd is odd plus odd is even. Because odd plus odd, when you multiply two of those, you should get a 1, and indeed g to the 2k plus 1 and g to the 2l plus 1 is g to something which is even. So that's one. What's the order? If you remember, the characters are is a set of characters is a group under multiplication, not under composition. We go to the same under multiplication, point multiplication. So what's the order of our quadratic character? It's really easy. So how many times you have to multiply by itself to get to the all ones character? Just two, because if you multiply, and it's multiplication, right? So if you multiply chi with itself, then you get a 1. And by itself, it's not a 1, so it's order 2. Good. Middle, just a quadratic. Quadratic adders will be useful for us. They always two. And now I'm going to state the theorem that we are going to use and then show the construction. Already know let's do the other way around. So having all of these, everything is ready. Let's find the, let's make what is the construction of the paradoxical tournament. Okay, so it actually will have no K move. So it defines it and asks the probability segment, but when it's large enough, it's K paradox. So in the construction, you won't see any K, which is confusing usually. Because I'm going to construct K paradoxical tournament when it's K. K will be kind of implicit, the size of it. So I'm going to define a diagram, tournament. Okay. So it's called the Paley tournament. So Q is again is an odd prime or an odd prime power if you want. I don't mind. So that's a graph. The vertex set is as you expect the finite field. And you have an edge from A to B exactly when chi of A minus B is 1. That's the thing. Odd prime power. So not 2 to the, otherwise, not false. Odd prime power. Prime power is. What? Yeah, it's not exactly. I mean, I should say something. I should restrict myself. I need Q to be -1 modulo 4. Hold on. So let me correct myself. I should have written initially. So Q should be so Q is hard. It's either 1 or -1 if you want 1 or 3 or 4. So I'm going to take the -1. Modulo 4. Q is -1 modulo 4. You have a residue of -1. Yes, okay. It's a yeah, it's actually one. Yeah. Just so I'm going to take Q, which is satisfy that, and it's not prime power.
No, I don't know.
So usually people write it like that. Ah, okay, later? You mean later? So you usually write it this way, or you can write it that way. That's it, later.
The total Q different
Right.
and A in A number.
Right, that's what I said. So you don't see K here. It's right? I'm just defining something, and what I'm going to show is that if Q is large enough compared to K, it's a K paradox. Like it's a mononomial. So if you are you're not just a paradox. What is the highest scale of paradoxical? That will depend on the size of Q alone. Yes. So, but why is it autonomous? I mean, it's not clear. So I need to make sure that if you have an edge, you have an edge between A and B, from A to B, you don't have an edge from B to A. Right?
B is quadratic minus.
Right, exactly. So let me just maybe a little bit differently, but the claim is this is a tournament. Tournament cause, let me say it more succinctly as possible. Chi, the quadratic residue of -1 is minus. extent. Once you have that, then I of A minus B is minus I of B. Because it's chi of A minus B times minus 1, and you have the homomorphism. So I will show that, but that implies this. Actually, chi of minus 1 tells you exactly whether or not, I mean, chi of minus 1 is exactly this number. It's 1 or minus 1, depending on the rest. And then I didn't plan on it, but let's do an exercise because I feel it's a bit fast. Let's do an example of it. So, what is chi of minus 1? I want to show that it's minus 1 in this case. Just make sure it's equivalent. So to see that, let's look at 1 for a second. 1 is G is the generator, or our generator, to what power?
0.
Good. So let's say Q minus 1. Okay, now I'm going to kill away. Okay. 1 is G to the Q minus 1. Right. Because, well, first of all, it follows because what I kind of said here. But if you remember last time, I said that in every group, if you take any element to the size of the group, you get the identity. Right, and that's the size of the group. And that's the multiplicative. Good. It's not complete. It's harder than mathematics. Okay. But now Q is the minus 1 over 4. Let me write. Q is minus 1 over 4, which means I can write it as like 4R minus 1. It's some R. So this means that 1 is actually, G to the 4R. So no, it's the other way around. And so minus 1, you see, because there is only like a bijection between this is a unique representation, not representation in the big presentation. Good, yeah. It's 2 to the R minus 1, because when you square that, you get that back. So this means that's the only way to write this function. And then you can see that minus 1 is not a quadratic. Because we said it's quadratic. So this means that I of minus 1 is minus. It's not a quadratic. Like chi of minus 1 is 1 exactly when it's a quadratic.
Why is the condition legal? Just
Okay,
because
clear?
minus 1 squared is 1?
Yeah, because there is a unique representation. If you don't like it, and I like it, if you don't like it, the way you actually should do it, like, more carefully, you should move it to the other side. And again, I don't like it as well. So that's equivalent to this.
And you have two solutions.
Right, and then you write it like that. Right? And because this is a unique representation, or maybe even because G is a generator, it's 2 to the R minus 1 power is not enough to get you to 1. G is a generator. The order of the generator is the good side.
So any other power than 1? Only
Yes, in a generator, by saying generator, I mean that its powers cover the entire. So if it, I mean, this is roughly half the group size. So if
So it will match like 1 to 1, never give the same element.
right, yes, because otherwise it won't be able to cover everything. The cycle for that
Oh,
point.
and 4 minus 1 inside of the group.
Right. So that means that's not 0. It means that is 0, and therefore that's the better way. I also like this. I kind of hide it under the rug, but that's how I like to see it. But it's this. You can also see the presentation. By the way, if we'll change it to our last one, right? Then it is a quadratic equation. Right, because when you have a plus 1, the minus 1, the minus 2 will just be 0. Then 1 is G to the 4R. So this means that minus 1, just ignore that, is G to the 2R, which means that minus 1 is a quadratic equation. So it's actually, what you really know is that this thing is exactly that number. This is minus 1 or 1. That's why I love minus 1 or 1 other than And so chi of -1 is exactly the residue of Q modular written appropriately for -1. Maybe we should do an example and just not to hold ourselves too much. We think it will benefit. CF7, 7 is good, right? 3 and 4, or -1 and 4. Let's see what happens. Let's look at F7. Let's first find all the quadratic residues. Because of that, cos chi of -1 is -1 under our assumption. We know that chi of A minus B is minus chi of B minus A. That's only just because, chi of B minus A times -1 is this thing. And then you can use the homomorphism. The product of the chi is the chi of the product. And that's -1. And in terms of construction, it means that if you have an edge from A to B, you don't have an edge from B. Right, so what does do? So what's going on in the technical part, or what do we do?
Like, what does this mean? Not have an edge
because we have an edge exactly if chi of A minus B between from A to B, exactly when this is 1.
-1 not an edge.
Exactly.
This
right. If we do 1, oh, we'll actually have like 4 edges. Right. Yeah. Yeah, okay. There. Except for the set flow sequence, which are not a problem anyhow. It's 0. And we don't have it. Let's see the example. I think the example will help us. So let's look at F7. This is an example. And the way there is a cheat to find the quadratic residues. Don't take an A and find its root. Just complete all squares and see what happens. So 1 squared is 1, 2 squared is 4, 3 squared is 2. We really don't have to continue on because 4 is -3. So we give it to again. You see, 1, 4, and 2 are the quadratic residues.
I was saying 1, 2, 4.
Right. Coincidence. Also, I know that 1, 4, and 2 are quadratic residues because I just hold them as quadratic. But it's not like I took 4 and try to find its coordinates. If you do, it's like harder. It means that you are a square of something else. So like 2 is a quadratic residue because it's 3 square. And 3 won't be because it's not going to be a square. It's called quadratic non-residue. So the quadratic residues are weird because they are square of. Also, technically, 0 is. Residues. These are the five. But if I just continue trying to generate more powers, I won't get anything because 4 is -4. The square between 2 and so forth. Right, so what I'm saying is that chi of 1 equals chi of 4 equals chi of 2 is 1, and chi of the rest 3 equals chi of 5 equals chi of 6. I was worried about is -1, and of course chi of 0 is. That's a quadratic residue table in this case. Always. By definition, a quadratic character of a field, when you define it, it's defined as 0. Otherwise, it's defined. I mean, it's really that's just extension of the fact that this is a multiplicative character, a character of the multiplicative. That's just by definition.
After definition?
Yes, because we said the character of a field is defined to be such as chi 0 is 0. When chi is coming from a character of the multiplicative group, so extend it also. So 0 it's not in the middle. No, because there is a little bit of this. The equation that we like, we don't want always to just not summing over the 0 or something, because sometimes you don't care. It's really a technicality. I don't think there's anything deep in it. Okay, so that's the graph. Let's try to draw the graph. So, well, let me Yes, that's necessary. Right? But it's if something is, yeah, exactly. Well, it's equivalent in terms of right. So let's see. So, for example, from 0, it's kind of annoying, yeah. From 0, because I want kind of a minus b. So from 0, you're going to have an edge. So I think of a as 0. So where does it go to? It goes to wherever chi of minus b is 1, which is where chi of b is minus 1. So this, because chi of a minus b, I asked whenever this is 1, to put an edge from 0 to b. So that's for each 0, that means just chi of minus b1, which is chi of b is minus 1. 5 and 6. And then you can do the rest. I think it's just one will be like, so you have a 1 step, 2 step, and it was like, and so, no, really different. I don't know. Okay, I hope this helped a little bit. Any question on what's the construction? So again, we take a finite field, size is 1s1 modulo 4. We define an edge from A to B if the difference between A and B in this order is quadratic residue, is a quadratic residue. If so, we put the edge, right? And that's it. We needed that to make sure this is a tournament. You don't have self loops because chi of a minus a is 0, it's not 1. Makes sense?
So that's the intuition beyond the open form.
Yeah.
I don't think 0.4 IQ okay.
Right. I mean, I think the fall comes from the fact that this is a quadratic residue. If you take a higher character, you really need to do something else. I mean, you're going to solve another problem. But then, I mean, this fall comes from the fact that this is an order 2 problem. Like there are two options. Q is hard, so there are really two options for Q to form one. I wouldn't have mind if only when it works when Q is 1 over 8. But you wouldn't expect that. But I consider this a technicality. So we constructed the graph. And what, yeah, that's a good point. And what we will show, I mean, it has no K encoding, and I agree it's weird. But what we will show now is that if Q is large enough, it's square constant to the K, then it's a K paradoxical. So, well, yeah, right. So we'll show this, right? So as long as Q is larger than this, maybe times a constant here, it's K paradoxical. Which something like that. So essentially from the largest K. So the proof is based on extremely heavy tool, which actually, I mean, in saying that, but it's a special case. So we can do it in the presentations, in the full-fledged theorems. But this one, for quadratic characters, and if you don't mind walking over all Qs, just some Qs, it's a 2-hour proof. We can do it in the presentation. It's also in several people. But it's not like a full course that you need to prove what I'm about to say. Maybe even a week about it doesn't really matter. Here's the theorem. Theorem the veil. Guy. He says the following, and actually said that kind of non-formally, informally in the first. But now we know things, so I can actually say it more formally. So let chi be any character, not just the quadratic residue. We are going to use it for quadratic residue. And let's say its order is f. So order in terms of how many times you have to multiply by something into one, no ones. The quadratic character it's 2. Okay. Now let's f of x. Now we're looking at polynomial of the field, univariate polynomial. B degree D for polynomial that cannot be written. We're going to exclude something obvious as c times h to x to s. So s is the order that we talked about. C is some constant, and this is some polynomial. Right. So what I'm saying essentially, you have to distinguish the constant. I have to say for it to be true. F is not just some polynomial to power s. In our case, f is not just a square of a polynomial. But other than that, f can be anything. Polynomial. So I'm saying that f cannot be written as some scalar times a polynomial. Yes. So it's not of this. Because then it will be obvious that what I'm saying is this. But it turns out that this is the only thing you have to explain. There is an attempt. Then, if you look at the sum, look at this sum. You run over all field elements, evaluate f at them, field elements, but distribution is the output distribution is actually kind of weird and unknown. Who knows what the polynomial can do, right? That's the point. About the question that they don't know when f is 0, f is 0 or not. I have a defined kind of 0. You don't want to exclude all a f is 0. And that's the only reason they. So what's going on here? What can you say about this, right? Right, you want it to be small. I mean, if f was like the identity, like the f of x equals x, or any linear function, then that would be 0. The quadratical residue is this. Because you're just going to go over all field elements. Kind of all field elements, half of them quadratic residues, half of them are not. It's also 0. But in general, just because I is orthogonal to the whole one side. Kind of a times 1, a 0. But what happens when f is like, say f of x was x squared, and this chi was the quadratic residue? That's bad, right? Because if this is a square of polynomial, we could say x squared, really. When that's a squared, it's always a quadratic residue. So that will always give you 1. It's going to be q or 2 minus 1 because 0 doesn't. So that's why I have to exclude that. But when the f cannot be written as a polynomial to the order of the character, this turns out to be really small, very far from q. Very clean bound. When d equals 1, you see it's exactly what we said, it should be 0. If you think of it as very small, right? It's much smaller than q. I mean, the way you apply it is when d is smaller than q, much smaller than square root of q. And so you can think of it as kind of as a standard deviation. That's how many like clicks you have of standard deviations. Maybe only for the quadratic character. They forgot the minus one when I wanted. Right, so it's a constant times 1 to the s. That's a good question. Not do constant. Because they are excluded. Linear is good. Linear is good actually. I mean, depends on the order of the card.
Yeah. You cannot take the trivial
That's true. Or maybe non-trivial card. Non-trivial. So it's one all the time. What do we want? No, it's like one. Five. H is F, C is 1. That's really deep. Okay. Interestingly, there are several ways of working that. There is like a more elementary ways and more wholesome ways of doing that. More than that. But one way to prove that is using multiplicity. Like, you know, the codes that we saw, that we said that we can move the rate from half to thirds, using also encoding in the code word derivatives. So this idea actually came from that proof. Because one proof of this thing is using multiplicity. So I don't need to say exactly what's going on. But and you can actually do that. I mean, not don't try to do it. You can actually present it. If you don't mind having some E escape in here, I mean, this is like one time. Okay. But if you don't mind a weaker bound, like maybe E times D times square root of Q, that's doable. A couple of hours. For some Qs. So we'll see, maybe we'll have the presentation at the end. But let's see how we can use that. It's actually not so far, but that's a strong theorem. I just want to make sure you understand that. It's considered by some like one of the most important results in mathematics. That's it. Because it essentially it follows by one such result, which is a proof of the Riemann hypothesis of the finite fields for algebraic curves. And that's, I mean, that you would expect to be counted as such. And then it's not trivial, but you can deduce from that the character. So but I'm not saying I won't say anything about any of them. I'm just going to use this here. Let's analyze our graph using this field. I'm going to show that will show that as long as well, I'm not sure exactly what we'll see. 4 to the k times k squared. Well, maybe as long as q is omega of that, that's fine. Maybe that's enough by itself, but I'm not sure. Then q is k paradoxical. Right, so k comes in the actually the analysis. Omega? Squeeze it. And leave room for the wrong paths. Because if you look at the data, how would you, well, first of all, how would you prove that? That's the easy question. The other question is, how would you come up with this construction? What you have in mind? Then, I think it's going to work out. So you'll see after you see a couple of those, well, I don't know, it's still kind of magical, but you kind of get a sense to why people might think that works. So let me try to convince you, when we're looking at this proof, that it's not so weird that it works. So again, even given this super strong theorem, the proof is not very nice. It's not obvious. Oh. So the point that I say is kind of algebraic thing. So you'll fix A, not like in the probabilistic method, fix A. Just fix A. But going to fix A, I want to show you that the this next dominates coordinates size K. So I'm going to show you that this X. Essentially, what I have to do is to find an X that doesn't do yet, but to find an X Final x, so the chi of x minus a is like 1. Because the chi of x minus a is 1, implying that x has range 2a. Okay, so now let's consider 3 cases. Well, like 2 cases, but all of them are split. So the first case, so according to x, in a is fixed, and I'm looking at x and 9 x. And now I'm looking at x that dominates a. So this is case 1. X dominates a. What can you tell me? What happens in this case in terms of chi? It's not a hard question. You know, how can you express it in terms of chi's? You have a formula and stuff. Let's start. Formula in A, what's going to happen? Right. Right, because if it dominates, it means that there is an edge from x to a to any, which is that by definition. The second case is where x doesn't dominate a, but I rather consider 2 cases according to whether or not it's for a good reason or for a bad reason. So for the bad reason, you should just x in a, it's not against. So that's the interesting x doesn't dominate a. What can you tell me there? What can you say?
There is a.
So, because there is an x direction, I can also write like that. There is an a that points to x. X minus a is. But that's the second case. And the third case is just x in a. Okay, this is a little bit tricky. What can you say here? There is a subtlety here. Actually, it's okay. There is an a, but let me just say it's unique also, it doesn't really matter. It's just x, right?
Yes.
So that x is 0. And that's like our. It's not really mysterious. It's x. And these are just some observation, like breaking down what the 3 cases according to chi. Just a side step, in the middle step. I don't want to do the entire job from the definition to what's going to happen now. So now comes the kind of, well, I don't know, the brilliant move came from the fourth move, like chess. Now I can just spot the fact that it was brilliant. Still, the brilliant move is to somehow algebra is on this. So I'm going to define, so I'm fixing A, X bar. I'm going to define psi of x as the product x plus a, x minus a, parentheses. So that's, I mean, I need a way, you know, in mathematics, you can't work with cases. You need one object that captures them all.
That's one point.
Right. Exactly. So psi of x, you see, if you look at the 3 cases, it will give you the case. So let's see. So what happens in the first case? So in case 1, maybe x. So if x dominates A, what can you tell me about psi of x? For the case of 2 to the k. Fine. So you see, at least, you know, I don't know, if you would have another 2 to the k, it's better. 2 to the k will tell you that x is dominates A. In the second case, what can you say? Exactly. You want this kind of separation. Because there is a -1. There is something going from A to x. So that should be a -1. So you multiply stuff, one of them will be 0. Very good. So that's a good thing. But the fact that they are distinguished, another little thing is that it doesn't really matter, but I have to say it. I don't know if it's true. In that case, and that's a little bit of tricky. A little bit tricky. What happened in that case? Right. So one option is the 2 to k minus 1. 2 to k minus 1 happens.
It's the worst.
Right. Exactly. 2 to the k minus 1 happens
when you dominate.
exactly when x within A dominates all of the other elements in A. Right? Because because he gives a 0, right? When you go all A in A and x is here, you have a 0 plus 1. Plus 1. But if he dominates all the rest, for every other A, you get a 2, 1 plus 1. So k minus 1, 2 is multiplied by each other. But that only happens if x dominates the other elements of A. It doesn't count as we found the dominating element of A. It's just you kind of almost dominating, right? So x dominates A minus x. That's this case. But in any other case, which is more typical, what will happen? 0. Because one of them will be minus 1. The one that dominates some little A that dominates x will give you a minus 1 here. And that will be a product of zeros. So it's just a technicality. That's really the interesting part. But what I say in mind is this versus those. But you have this little bit troubling term. Okay. Okay. So after the break, we're going to have like 4-line proof, depending how lazy I will be. I wonder if you can see it. I don't know. It's kind of hard to see. Okay, so let's continue. So we define this. Anyhow, we define psi of x to capture whether it dominates A or whether it's not for any reason. And the point is, looking at that, you want to find an x. No, now you can say I don't want to find an x for which x dominates A, but rather an x for which phi of x is large. Excluding this, I don't want. If it was 0 versus k, want to find an x for which phi of x is large. And there aren't too many x's like that, one goes to A anyway. So they're like most k things that would look like something which is large, but all of the other x's, they will be either large or 0, and large means So we want to find an x for which phi of x is large. And it's hard to move x by x. So what should you do? It's not always good. But you want some wholesome, like, you want to look at all x's at once, you want an x for which is right, just somewhere. Which I guess it's some sort of opportunity bound. Right. Maybe that's a good intuition. So you look at this thing. So technically, I can only go over x which are not in A. I can tell you just, it's easier like that. Because we are going to use the rail bound. Okay, so first of all, before putting this up, I know that this is, well, it's 2 to the k times the number of x's which, let's go again. So this is the number of x's which dominates k. Number of x's dominates k. And I would like to write it like that, but I still have to write it, because every one of those will be 2 to the k. But I do have to write, this annoying 2 to the k minus 1 option. So there is some, some b times 2 to the k minus 1, where b is either 0 or 1. Depending on whether A has an element within it that dominates the rest. And so B is like, B is 1 if and only if X dominates A minus X, or some X. There is there could be two of those. But otherwise, they're all of the dominating A. Right, so every X which is dominating A will contribute 2 to the K. So, maybe there are n of those. I want this number to be larger than 0. That's what I want. But there's also this contribution from this single element in A that may dominate all of the other elements in A. That will give me 2 to the k minus 1. I think of B as a bit. That's what they call it, B. Or bit. Okay, it's either 0 or 1. You should not ignore it. And the point is, I want to show that this is large. If you ignore that for a second, because it really matters, then showing that this is strictly larger than or equal to 2 to the k, even 0, right? we show that n is larger than 0. And with that, if I show that this is 2 to the k with 5. I want to show this is large. But this is large anyway. Okay, so let's open it up. So what is this? So by definition, sky is like this order. So the order is A, 1 plus sky of 1 over the other one. Is this thing? Again, the goal is to show that this is large. But I want to somehow get to a point where I sum quadratic residues of the. So the first thing to do is, the one trick in this thing is to replace the order of something. But there are no sums. Sum is a product. But you can write the product as a sum. Right? It's like costly, it feels like a 2 to the k kind of sum. That's fine. We're really for 2 to the k. So let's sum, forget about the outer sum. You can write the inner product as a sum of the all possible products. And because because of the one, right? When you open this thing, for every subset, parentheses you choose, you pick up the I x minus a. Otherwise, you get many. Other than that, you get many 1 times multiples 1. Multiples. Good. Now that's the situation where you like to be. You have like two sums. The first thing you should do is do that. That's rule number 1 is single unrest. Because it gives you another perspective of other differently. Also, you can't write the sum of the left cube. But okay. And in the so I replace those, and the product of chi is really just a kind of the product. That's the homomorphism. That's good. What can you say? What can you tell me about this thing? Polynomial, right? This thing inside the chi. What can you tell me about it? What it doesn't do? Right. So we don't want it to be a square. It's not a square. I mean, unless I is the constant is the empty set, then it's like 1. We'll do that. Once I is not the empty set, it's just a product of x minus a for distinct a's. It's not a square. We'll get at least one root, and no root appears twice. But f of x is not a square because it has distinct roots. But distinct roots. But it's a product of x minus a's, right? Unless I is the empty set. Then it's 1 distinct roots. Well, unless just make sure I is not the empty set. So the empty set, with one summing here, which is empty set, then you sum over few things which are 1. So the product of empty product means like 1. It's a unit element of the product. So when I is the empty set, you get a sum of q1s. This is still equal to q. This is just coming from the empty set. And the rest, well, the rest is in HA. It's exactly what the Weil tells us is bounded. Like this thing, in absolute value. So, as you go over all field elements, like whatever. It's exactly the situation with the phi. Right. So I want to prove a normal. So I'll do that. I want to prove that. So I'll do what? I want to prove that this thing is large. So I'm going to say, well, it's q coming from the first summon, and then you have like many summons, 2 to the k, maybe -1 if you want to. I mean, how many subsets do you have? You have 2 to the k of a is the set of size k, right? So for every I, there are 2 to the k of them. You can be slightly cheap, like more economical, but for any I which is there are 2 to the k of those, you excluded the empty set, but I don't mind. Even including the empty set. You have at most 2 to the k summits here. They will be, subtract things from Q, so I'll change the plus or minus in a second. But any one of these things is at most the degree of the polynomial, -1, I don't care, times square root of Q. So this is at least 2 to the k times the degree of the polynomial, k, times Q. Right, again, so you have the linear term, which is coming from the empty set, it's Q. And then you have, I want to show it's large. And then you add things to it which may be negative, but in absolute value they cannot be too large. Because they are at most the degree of the polynomial times square root of Q. Even though they are Q summons, they're only the degree times square root of Q. They are not Q. From the yeah, just using the way. But for each of the 2 to the k -1 subsets of k, which are not. And because for every subset, you have a polynomial here, and you sum over all field elements, the quadratic and the factor. Natural value. Natural value. So this means that this number could be too small. Right. Yeah. Minus the score.
Except that or negative.
You mean that? So the logic by fine. You only this one below. So I'm saying Q is the coming from I equal the empty set. In every other I may add something, but will subtract if at all, at most the quantity which is bounded by Q squared, by K squared. K is the degree of the polynomial. When you have like, when you know that Y and Z are bounded by D, then this is at least x minus 2. Could be larger. But if all of them are bounded in absolute value, then subtracting won't subtract much. Okay, and then really, I mean, okay, so that's about the thing we started with. This means that, let me just n times 2 to the k is at least that. And then maybe minus b times. But b is 0 or 1, so I can just take the whole things. 0. Then from here, you can kind of see that actually you can see something nice. Let's divide by 2 to the k. You can see that something really nice happens. So once you pick this thing to dominate those, once you pick like Q, which is like 4k k squared, right? You see, because the half is like really nothing. So you just want Q, you want this to be larger than that. So square root of Q to be larger than 2 to the k times k. So Q to be at least the square root of 4 to the k times k. Once you choose that, this way maybe like times 4 or 5 or 6 or whatever, this is roughly Q over 2 to the k. You can make, what I'm saying is that you can make this negligible. I mean, it is negligible once k is Q is sufficiently larger than 4 to the k squared. It's certainly larger than 1, or equal to 1, but actually it's Q over 2 to the k. Which is like, there's not only one dominating in this graph, there's not only one dominating element right? Roughly the right fractions. Like there's already one, in the heuristic of the one x will dominate k is 1 over 2 to the k. And you have Q of those. So you would expect Q over 2 to the k to dominate k. Like this is the kind of thing. 1 over 2 to the k is not the probability for x to dominate k. And in this construction, you also have this. Actually, it's stronger than just saying someone dominates. Actually, the right fraction essentially. You make this as close to that as you want once you take Q as a larger and larger. That's it.
What does the n stand for?
N is the number of x's that dominate. You want to show that it's at least one. But you actually show that it's a fraction.
Put this q, it's put the k.
So when I put q which is that large, or some constant that increases as you like, and this thing, these two are negligible compared to the R. As you can see that the minus one is the minus up is not a big deal. And then so you want this to be larger than that, significantly larger, whatever. Then this means that square root of q needs to be increased k times 2.
Yeah, I'm wondering why we don't continue, like, write the final expression as
Oh, yeah.
keep the
Now it's in terms of parameters. You can choose any constant and you get it.
why do we
Because to get that, so you want q over 2 to the k. I mean, at the very least, you want this. Because you want this not to negate everything. But once you have that, multiply by 2, you get much more. What you ask me.
oh, you have square root of q. Okay,
Yeah.
that's pretty big.
Yeah, exactly. And therefore, q is